Hi, it's been a minute. Let's talk about bloom filters. Why do we want to talk about bloom filters? Because I want to talk about invertible bloom filters. Why do I want to talk about invertible bloom filters? Because I want to talk about a new set reconciliation algorithm. This is a distributed systems channel. Let's reconcile some sets. But to get there, we need to understand invertible bloom filters, and to get to invertible bloom filters, we need to understand bloom filters. So we're going to do a crash course on bloom filters. We're going to get to the doorstep of invertible bloom filters, and that's going to set us up to eventually talk about that new fancy stuff. Cool. So bloom filters, what are they? Born 1970, data structure used for representing a set without keeping all of the elements of the set present. So let's pretend you have a list of 10,000 things. That's a lot of stuff. And what you want to test is, I have a new thing, and I want to check if that new thing is or is not already in the set. It's a pretty common trick. You do this in numerous programming languages. You would pump in, hey, hash map value, great. But to do that, you have to keep the whole thing in memory, which is expensive, right? A bloom filter will give you an answer to that question in two forms. It'll either tell you, no, that thing that you just showed me is definitely not in the set, or it is probably in the set with some degree of false positivity, which sounds bonkers the first time you hear about a probabilistic data structure, which is what a bloom filter is. The idea of like something answering probably in computer science feels really strange at first, until you start to realize the space and speed trade-offs that you can get with a bloom filter. Bloom filters can consume far less space than the actual sort of like total hash map you'd have to keep in memory normally. And that's the whole reason for building them in the first place. They originally came about in around 1970 to deal with slow disks, right? You could keep a bloom filter in memory, check that instead of going to disk, and now you have a really nice technique for testing set membership without actually doing an expensive round trip. And that's actually where they're still used today. There are numerous sort of variants on bloom filters all over the place. There's numerous different methods of getting around some of the shortcomings of bloom filters. And the challenges with them are they need to be parameterized. They need to be sort of like very specifically tailored and tuned to the use case in mind. And so to give you a sense of how that all works and how that emerges, first we're going to build a really quick bloom filter. Then we're going to talk about the parameterization, and ideally we'll get to the doorstep of invertible bloom filters and counting bloom filters and some of the other tricks that are around that. So first, let's build a bloom filter. We're going to build a bloom filter with 3 elements in a set, and we're going to put those 3 elements into the filter itself. The filter is a giant field of bytes, or bits actually. It will be bytes if it's multiple of 8, but in this case, what we really care about are the bits. And what we're going to do is when we go to add it, we're going to run an element through a set number of hash functions. And those hash functions are going to determine indices along that field of bits. And any of those indices, when you go to add it, you're going to flip it from 0 to 1. The bloom filter uninitialized starts with all zeros. And so in this case, if we have 3 elements and 3 hash functions, we are going to run the first element through all 3 hash functions. It's going to give us 3 indices along our bit field, along our bloom filter, sorry. And it'll flip all those to 1. We'll repeat that process for each of the 3. And the trick here is because the hash function, if you use the right type of hash function, it will distribute those elements evenly across a number of parts in the bloom filter. You're going to get a really nice property where as fields are coming in, unique stuff is going to set unique positions, and it sort of has a unique fingerprint according to the number of hash functions that you use to test if some new element is in that set that you've already prepared. So you've taken your 3 elements, you've added them, now you've prepared bloom filter, you know that bloom filter reflects the set that you're trying to be able to test. You bring this 4th element in and you go, hey, is this element in the set? What you're going to do is you're going to run it through all the same things as if you're about to add it through the bloom filter, but instead of flipping the bits from 0 to 1 or flipping it from 1 to keeping it 1, you are going to just check for all 3 of those positions, or all k number of those positions. And if any of them is 0, then you know that thing is definitely not in the set, because the process of adding it would have set all of those indices to 1. And that's where we get the definitely not property from. The probably is because you could get some set of elements in the set that set all 3 of those, or all of the fields in the thing that you're testing to 1 without ever actually having that element. And this is where the probabilistic nature comes in. If you think about it sort of intuitively, the size of the Bloom filter is less than the elements that it's representing. So there's going to be some loss of information inherently, right? And this overlapping is what's getting you the size guarantee, but it's also what's costing you the certainty. And so we can actually tune that in a Bloom filter. And that's part of what makes them sort of this exotic data structure, is you have to know in advance of creating the Bloom filter what characteristics you want it to have. And so this lovely Bloom filter calculator is a great way to sort of like go through the actual elements itself. In this like baseline example, it's showing you that for a Bloom filter that has 4,000 items in the filter, so a set of 4,000 things, and a very low probability, 1 in 9 million, almost 10 million, that you would have a false positive, which is to say the Bloom filter would say, yes, that element's in the set without it actually being there. You would need a 16 kilobyte width of Bloom filter. So that means you need 16 kilobytes of space of all these zeros that you're going to flip to 1 for those 4,000 elements. And you're going to need 23 hash functions. So every time you go to add an element, you're going to have to run that through 23 individual hash functions and get it out the other side. There are some tricks. If you use a really good hash function, you can actually take elements of the hash function and use that to set the k indices. And there's a number of other things you can do to sort of like make this more computationally efficient. But it is worth noting that like sort of in the main, you need some way of determining 23 elements of width to get these characteristics. And on the right here, you can see a graphing of different characteristics against each other if you were to modify them. So if you were to modify the probability in correlation to the number of elements, this is sort of how that would graph out over time. And so as the probability of a false positive approaches 1, this is the number of elements that you contain, and so on and so forth. One of the things that is worth knowing here is a Bloom filter just mashes all the elements in your set into this giant filter. You don't have any means of extracting the things that you put into that Bloom filter out, or do you? And that's what invertible Bloom filters do. There's actually a technique that came out in 2015 that will allow you to, given a Bloom filter and some specific sort of like important starting points, you can actually invert and get all the elements that are in the set. And that's what we're going to talk about next time with invertible Bloom filters, which again are the precursor for this really cool set reconciliation thing that we want to talk about in a bit. Again, we're more interested in Bloom filters as they relate to distributed systems. They're used really a lot in databases, file systems, things that want to do these really fast checks. Where we care about them are in relation to distributed systems. And for distributed systems, they're kind of meh. Bloom filters as they relate to distributed systems, I've heard it said to me that it just kicks the problem down the road, as to say, sometimes you'll see a solution in Bloom filter, when using Bloom filters in relation to distributed systems, it says, okay, we need to sync up the state of 4,000 items. And so we now need to know that like, okay, those 4,000 things should be on this node or 4,000 things should be on that node. Naively, we could just calculate Bloom filters on both nodes, exchange the filters instead of the full sets, and compare, hey, are they equal? Are they not equal? And we could then use those filters to test which things I have that you don't have, et cetera. But what that does by kicking the can down the road is as the set grows, so does the Bloom filter. And so eventually you get to a point where it's like, cool, we need to sync 1 million items. Well, now you're set, if we punch that in, if we wanted to do 1, 2, 3, 4, 5, 6, 1 million items, we now are going to have a 4 megabyte Bloom filter that we need to pass over the wire before we can start doing our checks. And you start to see how this gets really expensive really fast. And this is kind of where Bloom filters have hit a bit of a sort of major road bump when being used for set reconciliation. Is just, there's a lot to trade off. There's a lot of recomputation. There's a lot of round tripping that happens between two nodes that are trying to quickly arrive at, hey, what do you have that I have that I need? And what do I have that you need? Which we call a set reconciliation. There's lots of other places where you can use Bloom filters in distributed systems. Some of the best examples all often look like local node databasey looking stuff. If you had a gossip sub implementation and you wanted to make sure that up in application space, you're getting at most once message guarantees, that means you're going to often get the same message a lot from a lot of different peers. And you want to make sure that your application only sees that message once. A Bloom filter is a great tool for that, right? You can start taking the hash of every message you get, put that message hash into a Bloom filter. And then when a new message comes in, hash that, check it against the Bloom filter. Now you have a really efficient data structure in memory that is going to scale nicely and not make you hold on to every single message that you've seen in a hash map. So there you have it. Very quick overview of Bloom filters. Invertible Bloom filters are next. They're going to take a little while to explain. We're going to go into a little deeper detail, but I thought it'd be really nice to get this primer out talking about Bloom filters. Bloom filter, Bloom filter, Bloom filter. Okay, maybe we said it enough times. All right. Thanks so much.